So as we consider telescopes, there are two basic telescope designs. There are refracting telescopes and reflecting telescopes. Refraction telescopes uses the principle of refractions, meaning that it uses a lens to be able to bend and gather that light. This is the first type of telescope ever invented, and it's what Galileo used to discover the moons of Jupiter and the phases of Venus and all of that other cool stuff that he discovered. So the principle of refraction states that as light, in fact it's most things, go from one material, one medium, into another medium, that it will bend. Okay, now the bending is actually determined by the angle at which it enters. So if it goes straight into the medium at a 90-degree angle compared to the transition, then it passes straight through with no bending. But if it comes in at an angle as it goes from one medium to another, it will actually bend. You've probably actually already seen this and just didn't know what it was. So, for example, when you have a straw in a glass of water, it looks like the straw is bent. Now, it's not actually bent, unless you did something terrible as you smashed it into that water, but it's probably actually straight. So what's happening is the light from the straw is traveling through the water, then it transitions from water to glass. As it goes from water to glass, the light bends. Then, as the light goes through the glass and then transitions from glass to air, the light will bend again. So the straw itself isn't bent, the light has been bent, so the straw appears bent. This is the principle of refraction. So what we can do is if we shape a piece of glass just right, then all of the light that hits on the glass will then get focused, all gathered together into a single point, what we call the focal point. If you've ever played with a magnifying glass and caused it to go up and down, and you see that point grow and shrink until you get it to it's really small, and then you can burn stuff with it, hey, that tiny small point is actually the focal point. You've gathered all of the light hitting the lens into that one small point, and it gets hot enough, with enough energy, it can actually begin burning stuff. Now, to actually be able to see with your eye what's going on, we have to have a lens that is able to then focus the light so it can go into your eye so you can actually see what's going on. So we have the objective lens, which gathers all the light together. Then we have the eyepiece, which allows the light to pass into the eye so we can actually see what's going on. Now, another reason why magnification is not important in observational professional astronomy is because often we don't have an eyepiece. Instead, we have a camera that is set up at that point to record the light. Without the eyepiece, there is no magnification. You have to have both the objective lens and the eyepiece to get a magnification of the light. So instead, we actually just put a camera here at the focal plane where we're going to get the clearest images and then just record the light there. No eyepiece means no magnification. Now we have some problems with refracting telescopes. One of these is that as light passes through glass, it spreads out. Okay, we talked about forming a spectrum previously using a prism. Well, as the white light passes through the glass of our lens that's gathering it together, it also bends, which means that different colors of light are going to focus at different positions within the telescope. Blue light will focus at one point, and red light will actually focus at another. If you just take an image of this, it actually leads to this blurring caused by the different colors not focusing at exactly the same place. This blurring is known as chromatic aberration. Chromatic from color, and aberration because it's blurring. Chromatic aberration is this blurring because not all of the colors are focusing at exactly the same place within the telescope. Now, there are some things that can be done to fix this. For example, you can put a coating of another material on the lens that will tweak the light back so that it all then focuses together. But that's hard and expensive. Now, another problem we get with refracting telescopes is that we have the objective lens at the front of the telescope, where it's going to be pointing into the sky. Now, if you remember previously, we want bigger telescopes. The bigger the telescope, the better the angular resolution, and the better the light collecting area. We want big telescopes. Well, with a refracting telescope, that means bigger and bigger lenses, and that lens is at the top of the telescope pointing way up into the sky. I hope you can start to see why this is a problem. Okay, so we have this really big, heavy piece of glass way at the end of our telescope pointing around. This means we have a practical limit for how large a refracting telescope we can actually make. The largest one to date is about 1 meter across. That is a huge piece of glass, and it's a really pretty telescope. However, it's got problems. We're not going to be able to get much bigger than that. So our other type of telescope is a reflecting telescope. So in this case, instead of using a lens, we use a mirror and the principle of reflection. If we have a flat mirror, then the angle of the light coming in as it bounces off will be the same as the angle coming out. This is the principle of reflection. So what we can do is, instead of having a flat mirror, if we curve the mirror, then as the light comes in, it will then all bounce and again focus together into the focal point, gathering all of that light together. Okay, so instead of using a curved piece of glass, we use a curved mirror to gather the light. Now, there are 4 different designs for reflecting telescopes. The first one ever conceived of was the primary focus, or the prime focus. In this case, we have the light come down, it reflects off of the curved mirror at the bottom of the telescope, which then focuses the light. But notice where the focus is in the telescope. Okay, it's right there, which means that if you actually want to see anything, you stick your face right there, which then blocks all of the light from the telescope, so you don't actually get to see anything. So for relatively small telescopes, the first telescopes ever invented, this was not a practical design, and people knew it. Today, we actually have telescopes that are so large, it is possible to put a large instrument array at the prime focus without blocking enough light to actually do any damage to the telescope, or to the image, I should say. Okay, so we can actually use prime focus now, although generally it's not used as much. Well, realizing that we have the problem with the prime focus, Newton, the same Newton we talked about previously with the laws of motion and studying light, he realized that if he put a very small lens, or a very small mirror, not a lens, a very small mirror at the right point in the telescope, then the gathered light will then come out the side. And that's where you can put your eyepiece so that you can actually look through and see what's going on. This type of design is the Newtonian focus design. And this, if you've got a backyard reflecting telescope, this is probably the design that your telescope actually uses. Now, in more modern astronomy, we don't just want to look through the telescope. Trust me, we still want to look through the telescope. It's awesome. But we want to record images so that we can start taking data and analyzing and figuring out what's actually going on. Okay, well, you don't really want to put a big, heavy piece of equipment at the top and side of your telescope. That's going to lead to some difficulties. So to overcome that, we now have the Cassegrain focus. Okay, so it starts out in the same way as the other two. The light comes down and hits the primary curved mirror, which focuses the light. It then goes to the secondary mirror. But the secondary mirror does not cause the light to go out the side. Instead, it actually goes out a very small hole in the back. And because the hole is small enough, it's not actually going to block a lot of light. There's not a big deal. So now at the back and bottom of your telescope, you can now put your big heavy equipment, okay, so that it moves around and records the light all in good ways. Okay, so this is the Cassegrain focus. A lot of the really big professional observing telescopes actually use the Cassegrain focus. Okay, now occasionally the equipment that you want to use is so big, heavy, and bulky, it doesn't make sense to attach it to your telescope at all. Instead, you're going to want to set up this huge thing on the side of the room, or in some cases, it's actually its own entire room. Okay, well, you're not going to stick a whole room on the back of a telescope. So we have another way that we can do this. What we can do is we can set up the telescope so that the telescope sends the light to the big heavy equipment set up in the room. This is what the Coudet focus does. So it starts out in the same way. The light comes down and hits the primary mirror. The light then focuses onto the secondary mirror, and then it gets sent to the third or tertiary mirror, which is put in a very special spot within the telescope so that no matter how the telescope is pointed in space, that light is all going to go to the exact same place in the room. Okay, so we know exactly where the light is going to be headed. I only know of a few Coude-focused telescopes, and these are usually done for spectroscopy, very, very fine, detailed spectroscopy. Spectroscopy is where you take the light and then you spread it out into its entire spectrum. And if you get really, really good detailed spectroscopy, you're going to have very, very large specialized equipment. Reflecting telescopes actually helps us overcome both of our big major issues with refracting telescopes. First, the light does not actually pass through the glass at all. It's only reflecting off of the glass, which means no chromatic aberration. Also, our big heavy piece of glass, our primary mirror, is down at the bottom of the telescope, down near the ground, where it's not going to mess up the pointing of our telescope, and we're going to be able to cause it to shift around without a big deal. Okay, so we've overcome both of our big problems with refraction telescopes. Now, that being said, reflecting telescopes have their own set of problems. Specifically, for the light to actually focus all to the exact same place, we have to use what's known as a parabolic mirror. Okay, so it's the shape of a parabola, if you remember that from algebra. Okay, only a parabola will cause all of the light to go to the exact same place in the room, in the mirror. To the exact same place as a focal point. Okay, but actually producing a parabolic mirror is surprisingly difficult and therefore expensive. So, more often than not, we settle for a spherical mirror, which is not nearly as hard to produce. But because it's not a parabola, that light is spread out. The focal point is not exactly in one place. So because of that, we have slight blurring. Okay, this is what is known as spherical aberration. A spherical aberration. Blurring because we have a spherical mirror instead of a parabolic mirror. Now, there are some things that we can do. For example, you can just suck it up and spend the lots and lots of extra money to just get a parabolic mirror. That's one thing. Something else you can do is you can limit what region of the images you're going to look at. Okay, so if you look at just the center of the image, then you can get the center nice and focused, but the edges are going to be blurred. Okay, so you can limit exactly what part of the image you're looking at. Now, something else that can be done is to put in a corrective lens. Okay, so the corrective lens actually begins to bend the light before it hits the spherical mirror, but that bending earlier on allows all the light to then focus. However, adding a piece of glass means you now run the risk of chromatic aberration. So in the end, it all comes down to what is your science, what errors can you live with, and how much money do you have? These are terrible games that all scientists have to play. All right, so here is our third clicker question. Why do astronomers prefer reflecting telescopes? A, they don't produce chromatic aberration. B, the glass of the telescope is near the ground instead of up in the air. C, both A and B, or D, astronomers do not prefer reflecting telescopes. Go ahead and think about it, and we'll discuss in just a bit. All right, so why do astronomers prefer reflecting telescopes? It is C, both A and B. They don't produce chromatic aberration, and the glass is down near the ground, which means we're also able to get larger and larger telescopes. The current largest telescope in the world is somewhere around 10 meters across. The mirror is 10 meters across. And there are a couple of other telescopes that are currently being built that are around 30 meters across, meaning these things are getting as big as a football field. We would not be able to do that with a refracting telescope. It's only possible with a reflecting telescope.